Good evening, everyone. Let's start off. Great. We'll be starting off with magnetism. Again, another important one. Like I said, the entire electromagnetism chunk is important for the advanced perspective. So let's go ahead. We'll start off with this. Hope everyone has gone through the notes. It's important you go through the notes. So we have a particle here which is projected with charge q, mass m. It's projected with speed u. And this thing, right, started going in a parabola. Y is equal to x square. So this is the path of the charged particle in the presence of a magnetic field. So there is a magnetic field B in the region. It's not going in a circle, it's going in a parabola. That means this B is not constant, B is actually changing. Find the magnetic field as function of x. So here it is given B bar is varying with x. How do you find the magnetic field as function of x? Others do keep your cams on. There is one formula you need to know. You know that it gets over in a step. If you don't know that, then you're one. Think, take a minute, then I'll show you. So there is a formula for radius of curvature, if you guys remember. 1 plus dy by dx whole square whole to the power of 3 by 2 by d square y by dx square. This is the mathematical formula for the radius of curvature when the equation of the thing is given. So you can find this in circular motion. We have done here. This is the proof. This is the mathematical method for the radius of curvature. So this is the formula. So if someone gives you the equation of a curve, we can use this to figure it out. So this is page 110. I'll leave it there. Useful thing. So if you know the equation and you just want to find the radius of curvature, you need not do anything. So, and when this guy is going in a circle, so that formula is still valid. The radius of curvature is mv by qb. Now remember, the speed of the particle will not change since the work done by magnetic field is 0. So the reason the radius is changing is because of b. There, you're done. You know the radius, substitute dy by dx, finish it off, and you get b from here. mv by qr. Easy? Right? So that is one way to play this question. But you need to know the radius of curvature for this thing. This comes from circular motion. This is a mathematical thing. Now, another variation of this, same thing. If I say charge q, mass m, projected with speed u, and let's say the magnetic field B is equal to B naught T. It is changing with time. Now, in that case, it will again start changing This delta is your deviation. Find delta as function of time t. So the previous one I'm changing with position. Here I'm changing with time. You know what is this question like? किया था हमने recently. Center of mass में this guy. Remember? The side thruster wala rocket. Something similar. So this and that, they have a lot of similarities. There also, if you remember, the speed was always constant because the force was perpendicular. Here also speed is constant. Same the question. Particle is projected with speed u. Find the deviation as function of time t. So how we do? So we know the radius is mv by qb. So v by r is qb by m. Actually, you can get omega directly. So this is your omega, which is nothing but d theta by dt, which is qb naught by m into integrated on both sides. We'll get theta is equal to qb naught by 2mt square. Easy. There it was actually a little more complex in that rocket one because the mass was changing. You're getting in terms of ln and all that stuff. So easy version, but yeah, you can have stuff, changing with b, and this will work out like this. Another variation of this question. Let's see whether you remember this or not. So we have a region here with a d. This is x is equal to 0. This is x is equal to d. And here the magnetic field is equal to b naught into 1 plus x by t. The magnetic field is increasing linearly. You took a particle q and m and you projected with speed u. So it enters here, it starts deviating, and then it comes out. Find delta. You must have done the standard equation if you remember. If the b is constant, then sine delta is equal to d by r. There was a standard question like that. We are just playing with the particle motion for now. They can ask you a lot of questions. Find the average force, right? Find the deviation or find this vertical displacement kind of stuff. So yeah. Here I still gave it like this. Huh? I can even make it enter at an angle theta. That's okay. There is just one thing you should know. Like if you know that formula, it is done. We not did you take B average God? We have. Did you take B average or something? No, you integrated it. Okay. Can you find the average force? Average force acting on the particle for the entire time interval. How do we do this thing? So I won't be able to teach you the whole thing, but you should definitely go back and check out here. This is the theory, everyone. Check. So this is how we started the theory there. We said a particle is entering at an angle alpha and leaving at an angle beta when B is constant. Okay. So this is page 21. I'll write it down, but listen. Then we did this derivation. We said, okay, this will, since B is constant, it will go in an arc and the center will be outside. We did little geometry and everything and we proved here. This is the standard result when B is constant. Sine beta minus sine alpha is d by r. Beta is the final angle, alpha is the initial angle, d is the distance between the thickness of the region, and r is the radius, which is mv by qb. This is the formula for one region, okay? Then we said, okay, and this is the average force you can find here, but okay. Then we said, okay, what if you have multiple regions? Look at this thing, huh? B1 is inside, B2 is outside, B3 is inside, B2 is outside, and so on. Now you can actually use this formula multiple times, and you'll get a telescopic function. Sine alpha 1 minus sine theta 2, sine alpha 2 minus sine alpha 1, and so on. When you add this is the summation. So sine alpha final angle minus sine theta initial angle is d1 by r1 minus d2 by r2 minus, because the field direction is changing. If all the fields are in the same direction, I would put all plus signs. So you don't have single region, but you have multiple regions. Then we said even better. What if the field is changing with time? Now just look at this derivation here. If all are in the same direction, can I just put sigma di by ri? Right? And sigma becomes integral. So there, the formula becomes like this. So whenever b is changing, this is the general formula for deviation. Sine theta final minus sine theta initial is dx by r. And r is mv by qb, and b is changing with x. You can just dump it there and integrate. So you can directly can't jump into this question. You need to know for n sections. And from n sections, you will know, okay, I can do this. That's what makes this question an advanced question. If you know the result, it looks easy, or else you have to literally derive the whole stuff. Right? So you should definitely go through this. So this is page 21. Yeah, that's one really good one. So you're done, right? So R is mv by qb, dal do and integrate kar lo. Matlab, I think you'll get in terms of ln, I guess here. So doable. For the time, I think, yeah, for time, we have to use this again, b of x, and we have to get the delta in terms of time and integrate, and that will be a little complex, but you can check it out. All clear with this? Then this is another pretty good one. If this comes in the exam, you won't have time to derive. I mean, even if I do it pretty fast, I think I'll still take around 5-6 minutes. Right? You can do it fast, but it's not thing. So you should know. But if you have not seen this before, there's very difficult you will solve this. So we have a particle here, Q and M, initially at rest, U is equal to 0. You have an electric field E, and you have a magnetic field B. Hope you guys remember this question. Right? So something happens here. So describe the motion of this particle initially at rest. Because of the electric field, this will start moving up. And because it starts moving up, the magnetic field will make it turn. So describe the motion, right? Find the maximum y coordinate. right? So I can literally ask you find the x and y coordinate as function of time t. That will take care of everything. I can ask you maximum speed. I can ask you after what time will it touch the x-axis again? Where will it touch the x-axis? We can ask a lot of stuff. But think about this. I'll give you 2-3 minutes to think. We have done this in the notes, and then I also in the notes, right? I told you there's a way to do this in a much faster and easier way. But first, you figure out. First, try to draw the path of the particle. First, try to just draw the path of the particle and figure out what the hell is this. You have an electric field and magnetic field, both. This is what I'm saying. There are certain questions in physics. You see the question and you should like, oh, this is that. That should come into the mind immediately. You can't do that. You're stuck in the exam. Because once you get that idea, right, and when questions are framed on similar concepts, you will be very fast. I'm not sure how many of you got that idea. When you saw this question, you felt like, oh, this is that. And you know what to do. I hope you got the trajectory at least. So if you just try to draw the path here. So initially, because of the electric field, it will try to go up. But the moment it tries to go up, the velocity v is this way, the magnetic field is out, the magnetic force will be inward, that will start bending inwards. So the higher you go, the faster you go, because electric field will increase your speed more and more. Right? But as your speed increases more and more, the magnetic field will be more and more. So you'll start turning back. Once you start turning back, you will slow down because you're going opposite to the electric field, and eventually you'll stop again here. And then again you will start. You'll just keep jumping like a monkey or grasshopper. This path is a cycloid. This is a path of a cycloid. Now, I'm not going to show you the derivation here, but I'll tell you how to, if this question comes without doing the derivation, how to get the result. But you should definitely check out the derivation. That will teach you a lot of things on integration. This was there. Exact same question. You can see that. Draw the trajectory, speed, blah, blah, blah. Yeah, if they ask you speed, right? This thing I taught you in mains revision. This is the most easiest question to find speed. Can you find the speed at x comma y? Try. I'll give you 20 seconds. That's it. That much time will give. That's a standard question. I don't even care what is the trajectory. You can find the speed without knowing anything. If the particle is starting from rest from origin, find the speed of the particle when it is at x comma y. Do it in 30 seconds. I need not know what is the path. I need not know anything. That would be the easiest one in this. And that's a very good mains and bits question. By the way, you don't need it for our question right now, but yeah. Hmm. Mm-hmm. So how do you find this? Look at this. I don't care where the particle is going. So this is x comma y. So the only force that can do work is electric field. Magnetic field will never do work. So work done by electric field is EQ. Vertical direction displacement is y is equal to half mv square. That's it. That's your one single statement. Work done by all forces is change in kinetic energy. Since the magnetic field cannot do work and the electric field is always in the vertical direction, you should take only the vertical displacement, isn't it? So EQY is equal to half mv square. That will give you the speed in one equation. That's why I said it is a very good question. And you don't even need to know what is the path. Anyway, so let's see how to derive this. So just follow through. I'll just show you the steps. You can check out the derivation later on. So this is how we started. We said after some time t, let the velocity be as vx I cap, vy j cap. And then we said force. Remember, this is the Lorentz force, q into e bar plus qv cross b. Then we found ax separately, ay separately. And these were the initial conditions. Initially, velocity was 0, Vy was 0, Ax was 0, but there is an acceleration initially, Eq by m, because of the electric field. These were the initial conditions, and these are the two equations. And then we substituted here, we differentiated this guy, and then dvx by dt became ax. That ax, you brought it and kept it here. So you differentiated it, you got an ax there, you substituted there, and you got an equation which is looking like an SHM. And then we got Vy, then we got initial conditions there. This is what I got Vy. I took this Vy, substituted there, I got Vy, and I got y coordinate, and I got x coordinate there. And when you solve the entire stuff, this thing actually looks like an equation of a circle which is moving. And when you actually observe this thing looks like the motion of this particle looks like a motion of a particle on a wheel which is rolling. This motion is called a cycloid. I hope you guys remember this. So cycloid is actually, right, when you take a wheel and roll it on a floor, and if you choose any point on the circumference, the path taken by that particle is called a cycloid. So this particle exactly behaves like that. We proved it, okay? We're not assuming it. Mathematically, we proved it. So whenever you get this question, what do? You replace this whole question with a circle with speed v0 and omega. What will be the speed v0? E by b. If you look at that, is the dimensions, isn't it? E by b is there, right? And omega is your regular omega, qb by m. Radius will be v0 by omega. There you got everything you want to solve. So if they ask you what is the maximum y coordinate, what is the maximum y coordinate? 2r, right? The diameter of the circle. At what point will it go and touch the floor? 2 pi r. In one revolution, the wheel will travel a distance of 2 pi r. What is the length of this one arc? 8r. The distance traveled by the particle is 8r. This derivation, we did it in kinematics, in case you don't know. Be careful between displacement and distance. When a wheel is rolled on a floor, any point on the circumference will travel 2 pi r displacement, but it will cover a distance of 2r. You can literally convert this problem into, a wheel rolling on a floor, and you'll be done. You can skip all that integration, it works. Is this making sense? You should go through this. If this comes, this will be an advanced paragraph or a matrix matching or something. You can ask a lot of stuff because you can see, right, it is jumping between kinematics. There's a lot of math, magnetism, everything is there. So this, you should definitely check it out. Page 36. But I'll just put on the main things again. So whenever you see this kind of a question, right, you can replace this with a wheel. So this point is like this point here on the floor. And you will exactly see the same motion here. I'm not drawing up to the scale, but yeah, you got it. It looks like this. So that point is going something of that sort. So you can assume it is a wheel going with the speed v and rotating with omega. So you can take this as the data there. Speed is given by E by B. Right? That is 1. Omega is nothing but 2 pi by time period. And what is the time period ka formula for a particle? 2 pi m by qb. That comes from your regular magnet or something. So qb by m. So what is the radius of the particle? B by omega. B by omega, which is E by B, and omega is q b by m. Me by qb square. So that's your radius. So then you'll get everything there. So this point will be 2 pi r comma 0. This height will be 2r. The maximum speed will be how much? 2 times v, which is v plus r omega, which is 2v. What else you want to find? You can just compare with the circular motion. You can get everything you want. All clear with this? So you can literally skip that 2 pages of integration. It works. Any doubts on this? So you want, you can check out the derivation, but yeah, as long as you know these two things, everything falls in place. This entire arc length, right, is this distance is 8r. You should definitely go and check out in the kinematics notes. So I'll put that also as a reference. Wait. This question is the 11th question here. We actually did it as a function of theta. 8r sine square theta by 4, where theta is the angle rotated by the wheel. This is page 41, kinematics. I think, yeah, you can get all that stuff there. But now, exam they won't ask like this because it has become very standard, right? So I hope this thing got loaded. They'll ask like this. Let's see how will you do this. I found this question somewhere. When I saw this first thing, it clicked over, said, oh, it is looking like that. And then I felt, okay, this is how you also should feel in the exam. If you can't feel that, right, oh, this is looking like that, you can't solve. And that's what I keep saying. You should be thorough with your notes, derivations, and all that stuff. Not because my notes is something great or it is awesome and everything. It is simply you need to cover enough models. When your brain has enough models and ideas, it will be able to relate to different things. That's it. It's fine. If your classes notes is good, it is better. Follow that. Doesn't matter. But stick to one thing and do it thoroughly. That could be any material. Think I'll give you 3-4 minutes. Let's see how will you figure it out. By now you must have understood this and the previous thing. Whatever I told you is same. How it is same is something you figure it out. And there are 4 options. Figure out what is the right answer. I think वो last वाला थोड़ा cut हो गया, but ठीक है, we can derive. The magnetic field is into the plane. That's a cross. Everything is there and the question is there. So you can read. You can't ask anything more there in the exam. The examiner will not say, I have no idea. There. If I'm writing a question, you can ask me because I'll skip sometimes data. This is everything is there. This is one thing you need to understand. You see a question, you can't ask anything like, oh, hey, figure out. You assume whatever you want and you figure it out. Because examiner will not be able to help you out. I think these are multiple choice question, right? This is a more than choice question. Get everything. But isme there is one question you can do without knowing any shit. Without knowing any damn thing about what I taught you, you can still do one option in this. Anyone can tell me which option is that? Which option? The third one. So if you have no idea, and if there's a more than one choice question, chup chap, at least I'll mark that and I'll go ahead. At least I'll get 1 mark. I'll not try to act too smart. If I don't know, I don't know. I'll go ahead. I'll find something easy somewhere else. How do I know that is the answer for sure? Same story. Work done by magnetic field? 0. The only person who can do work? Gravity. mgh is equal to half mv square. That is the only option there for speed. Because c is the time when you touch the ground, isn't it? So this guy is going something like this. So c is for sure. Not much we can guess. What about ABD? Seriously, if I don't know how to do this question, if I can figure out C, I will go ahead. I will just mark that. I'll get 1 mark. I'm happy. I'll go do some other easy question in some other chapter or some other subject. Be ruthless. Every mark counts. In 2016, yeah, 18, there was one question. So the question was pretty interesting. Matlab, you must have seen that, right? वो disk था बीच में एक slot था, find R and all that stuff. So some of your seniors now what they did. So the options were interesting. Matlab A, B, C, D. When you look at the options, right, you can eliminate two options. If answer was A here, then B is the answer here. If this was B, then A is the answer here. This much we can say. Problem, we don't know what is the answer. Now, people who are smart, what they did, they marked both A and game. At least एक तो right होगा. So -1 +4, you'll get at least 3 marks for sure. Right? So seriously, things happen like that. You know, people said, okay, I said, they're like, sir, I don't know how to solve this question, but this much I realized C and D are wrong. I can clearly see this option A, so I will get this answer, and that is this. I'll mark both A, I'll get 3 marks, I'll go ahead. Why do you need to use my brain and waste my time? I'll go and do some chemistry ka question which are easy, or maybe physics mein kuch easy hai, I'll do that. End of the day, total score matters. So exam mein, right, your mindset matters a lot. That's why I keep telling you, you have to be calm, and you need to be, when the paper is tough, you need to become more calm. Because everyone is panicking and messing up, you just need to find some easy ones here and there and do it. Because if the paper is tough, everyone is going to get slaughtered. You just need to get less slaughtered. Bas. You can't escape that. So did you guys figure it out? So first thing, the comparison, G looks like EQ by M, isn't it? If you replace that electric field with gravity, electric field is giving how much force? EQ. How much gravity is giving mg? So can I say gravity is similar to EQ by m? Right? And now flip the whole question. If you flip the whole question, the question looks like this. We have an electric field acting down and we have a magnetic field like this. We have a charged particle here, Q and M, starting from rest. So this guy will come down and this will go like this. This is your cycloid. Now this question has become like the previous question. Make sense? So this particle here, which is falling, will actually go like this. So this is actually forming a part of a cycloid. This is your point C. What do you want to find? Distance traveled by the particle from A to C. Now again, information, right? What is the velocity? Velocity is E by B. What is E? E is nothing but mg by q. Again, you can just replace it. It works. Omega is qb by m. Right? Actually, इतना करने का भी जरूरत भी नहीं है. I know everything. Isn't this supposed to be 2r? That height which is given, he's grazing. So he's saying indirectly this is 2r. This is h, which is nothing but 2r, right? So I know the radius. So radius is h by 2. So from A to C, what is the length of this curve? So from A to C, this curve will be 4 times r. And r is h by 2. So this is 2h. First option is right. Making sense? And from here to here, this is half circle. So you're asking this distance. How much is this? 2 pi r ka half, right? So pi r. But what is r? H. R is h by 2. So that's pi h by 2. He's asking from A to C. So yeah, that's gone. What about the time of flight? Half of the time period? Isn't it? For you to, it's like a particle completing a revolution, isn't it? So time taken from A to C is half of the time period, which is pi m by qb. I don't know what is that. So, but looks like a 2 or something there. So if I say this is qb, then yeah, that is also right. Is this clear now? You need not even do all that v and all. You can clearly see this height will be the 2 times the radius. I got the radius from there h by 2 and I can get everything. Are you clear with this? There. So, but you need to know that whole story there. So AC and any doubts on this? Clear? So that is one way to play around. Next thing. Now, there is some concept I want to teach you, cyclotron. You guys know this? So what is a cyclotron? I'll just give you a basic idea there. Experiments, this will come under that. So cyclotron technically is not there for mains, but this is the top view of a cyclotron. This is your side view. This is the schematic. So there are a lot of pictures there. I'll explain you how. The working is pretty easy concept. You should just know when there's a cyclotron, you should know how it works. The actual one looks something like this. The Large Hadron Collider and all this, so these are pretty huge ones. That thing has a circumference of 1 to 2 kilometers, and inside it looks like this. You can see the piping and everything inside. You literally have small vehicles inside where you can travel inside. So the largest one is in that Geneva, Large Hadron Collider, LHC. They do that all that experiment stuff there. I think when it was constructed, it was around $6.5 billion. I think this was in 2002 or 1. I was in school then. I still remember. So there was something came in the news like, when they start the Large Hadron Collider, there will be mini black holes. So the scientists told, when this thing starts, there is a chance of getting microscopic black holes, which will evaporate in, immediately. There is no problem. Itna bola tha. But you know now what newspaper does? They only took that first word. It creates black holes. Bus. They started messing it up. Once this thing starts, the end of the world, black holes will form, aliens will come from there. Kuch bhi likh raha tha, matlab. And in the school, right, we started shouting to the teacher, like, we want holiday, we want holiday. I think I was in 8th or 7th, I guess. And teacher said, why you want holiday? I said, sir, teacher, someone told tomorrow, the world is going to end. So you want a holiday tomorrow. We are such idiots. World is going to end. All you bother about the holiday. We didn't get a holiday. The world didn't end. So anyways, so let's see what is the experiment about. So the idea here, right? So let's see the side view. Okay, we have a big magnet on the top. We have a big magnet at the bottom. So this is generating a magnetic field up and down. Okay, this is the top view. When you see there's a magnetic field. So you can see there are all different setups there, side view and everything. So between them, right, we have two plates here. You can see these grooves here. So there is a small plates between them. These are called Ds. So Ds are nothing but two capacitor plates. Simple like that. Getting it? So what happens in this experiment, right? I'll draw a simple schematic, say. We connect this to an AC source. Why AC source? We will talk about that also. Think of like this. So we start the charged particle here. Initially, it is at rest. So let's say initially this plate is positive, this plate is negative. Now, because of the electric field, this particle will accelerate. It will go faster and faster. It comes out. So we have that spacing there. Once it comes out, we have a magnetic field in this region, B, and magnetic field here, B. So outside the D's, there is a magnetic field. So they do that, how it is done and all, don't worry about it. Once it comes out, because of the magnetic field, it will start going in a circle, QB cross B. It will do a semicircle and it will enter again. Now, once it enters again, imagine if you use a DC battery, what happens? This will be still plus, this will be still minus. This time the particle will slow down and stop again, isn't it? But we want it to speed up. So what we will do, we will use an alternating source such that by the time the particle reaches there, this plate will become positive, this plate will become negative. Now, how can you do this? We can do this because luckily the time period of the particle 2 pi m by qb, did you observe something here? This is independent of velocity. That means no matter how fast you go, you will always come back to the same point in the same time interval. That means the frequency is 1 by t is independent of the speed. Whether you go fast or slow, you're going to reach the plate in the same time. Making sense? So every time it does an half oscillation, this thing will go from plus to minus and minus to plus. So this will also be the frequency of the source. So you have to get a AC source which will have the same frequency as this thing, QB by 2 pi m. You're getting it plus minus. So what will happen? Now again it will go faster. Now because the speed is more, this time you'll go in a bigger circle. But luckily time is still t by 2 only, isn't it? So by this time, again, this will become positive plate, this will become negative plate. So by the time this thing completes one full 360 degrees, the source has become plus minus to plus minus again. So that is one frequency. Is that making sense? Now again, speed will go up. Again, it will go faster. Again, speed will increase. Again, it will go faster. And this will just keep going on. So what stops you? Like what is the limiting factor here? The final speed, right? R is equal to mv by qb. So the limiting factor here is the radius of the accelerator. So the final speed of the particle will depend on how big is the accelerator. So the bigger the radius, the faster the speed you can get. Making sense? So if you make a small particle accelerator, the speed will depend on R. So currently this particle accelerator which we have, this thing has a circumference of around 1 kilometer. And this can reach speeds of around 90, 0.99 C. C is the speed of light. Now they're trying to manufacture, construct a something which is 4 times bigger than this. So the problem is that. And what about the thing there? So if you take the distance between them to be, you can also do something like this. Let's say if it crosses the D n times, if it crosses the D n times, you need not use a sinusoidal source. You can use a constant voltage source, which is just alternating, right? Then if you cross n times, then the voltage will be n into voltage must be equal to the change in kinetic energy. Making sense? N into QE. Q, every time you cross the voltage source, N into Q into voltage, you get an extra energy of Q into V. If you cross N times, you'll get an energy of N into QV. That is equal to half M U square. Is that clear, everyone? Is the construction of cyclotron clear? Right, you can go to NCRT, right? They have a full paragraph on this. You can just read it. You really don't need to know much about this. That is the whole idea about it, right? This is the construction, this is the working. One of the drawback of a cyclotron, right? You cannot accelerate small particles like electrons. The problem is once you start going faster and faster, relativist effects starts coming. Relativistic effects, come into the picture. The mass of the particle becomes m naught by root over 1 minus v square by c square. Relativity. So once you start reaching close to the speed of the light, the mass will start increasing. If mass increases, frequency will change. If the frequency changes, this will start going out of sync. So this is one of the drawback of a particle accelerator. So once the relativistic effects start coming into the picture, this becomes problem. That's why we don't use electrons in an accelerator. They are really not that great. So if M changes, F changes. So that is one of the issue there. So cyclotron, you should have an idea about it. So let's see if you have any question. I think I have one. There, let's do this thing. This is a question actually from an Erido, slightly modified, but yeah, this is a Erido question. Let's see. So how do we do this? Let's first get the data first of all. The radius r is given. So r is equal to m into u by qb. So I know the speed. Hmm, the second one, let's say it crosses the d's 10 times. So n into charge into voltage is equal to half m u square. So get u from here, take that and dump it here. QBR by m. This will give you n. So I know you're crossing the d n times. Now what? Now what? So this d is right. Remember that frequency thing? So if the frequency was f, so remember one thing, huh? This charge, right? The voltage is changing only when this thing is inside, isn't it? So every time it crosses, how long does it take to cross this thing? The total time of accretion of each ion inside the cyclotron. So you're neglecting the gap between the D's. So and also, I think you can get the time period from this thing. How much is this? Every time you make one circle thing here, you cross the D 2 times. So the time must be n into t by 2. So for every crossing, it takes a time interval of t by 2, isn't it? And that will be how much? Now, again, you might be thinking, you're accelerating only when you're inside. Be careful. When you're going in a circle, even then you're accelerating, isn't it? Centripetal acceleration. Hope you're getting it. The general thing is this: people think, oh, you're accelerating only when you're between the D's. First of all, he said the distance is negligible. We can ignore the time. But what you're forgetting is when you're going in a circle, even then you're accelerating, isn't it? So even that is counted. So if I actually want to find this acceleration rate, I need to know the distance between them. So that is not given. We can ignore that because it is too small. So a particle going in a uniform motion is also accelerating. So this each one will take a time of t by 2. So if you're crossing it n times, then the time will be n times t by 2. And t is nothing but 1 by f, so n by 2f. So particle in circular motion is also accelerating. He never said find the time spent between the d's. An interesting question would be like this also. Find the total distance traveled by the particle. How will you do that? Any ideas? Basically, you'll get a circle, you'll get a bigger circle, you'll get a bigger circle. So every time the radius is increasing, right? And you also know the number of turns, no? So can I do like this? The first time you cross, what will be the speed? Q into V is equal to half m u1 square. You know the speed, from here you can get the radius. So r1 is equal to mu1 by qb. Second time when you cross, it is 2qv. Now the speed will be half mu2 square. Now the radius will be r2, which is mu2 by qb. When you cross the nth time, the speed is nqv. Half mun square, and the radius will be mun by qb. And the distance traveled will be every time you're completing an half revolution. So instead of 2 pi r, we'll use this thing, pi r1 plus pi r2, so on till pi rn. If you add them all up, you get the distance. Sure. Frequency of the ions is the frequency of this thing. So there, now frequency is given, right?
Why did we take by 2?
Array, this is only half revolution, array. You cross the d 2 times in one oscillation, na? If you're crossing n times, मतलब frequency कितना था? N by 2 था. N by 2 of a time period, isn't it? Got it? Every one circle, you cross the d 2 times. So double था वो. So be careful with that. In one circle or one revolution, you cross the d twice. All clear with the cyclotron? So this is one experiment you should definitely have an idea about. Let's see one more. This we did in the notes. This is the top view. There is no gravity. E is equal to 1. Magnetic field. We have a particle here projected with speed u, charge q, mass m. R is equal to mu by qb, and this distance here is r by 2. Meaning, see, the moment you project the particle, technically speaking, it wants to go in a circle like this. But you kept a wall in front of it, so you're going to collide, but E is equal to 1. So it will bounce. Find the time interval between two collisions with the wall. Draw the trajectory. Draw the trajectory. Find time interval between two collisions with the wall. No gravity, yeah? There is no gravity. This is a top view. Basically, it is on a smooth floor. Oblique collisions, magnetism. T by 6. Okay. I don't remember. Could it be? Let's see. ये तो notes में है. I think that is wrong though. I remember it is little greater than T by 2. Try. I'll give you a minute, 2 minutes, 1 or 2 minutes. It's a good one. It's not difficult. This is a pretty good question. They can, something like this, they'll ask not because, it's not too tough, doable. But you have to be careful with the picture and draw arms and you will see everything. In that sense, it is a क्या बोलते हैं उसको? It's like, people say na comfort food. It's like that. It's a comfort question. That looks right, Vihan. Can you tell me what happens if E is 0? First do this. First do this. Yeah, one answer. We have two answers. Daniel, right? So, what's happening here? Bit of a geometry. So this distance is r by 2. So QB cross B. So the force will be this side. That means for this particle, the center will be somewhere here. So using that point as a center, try to draw a circle. And you collide here. Right? So this height is r by 2. This is r. So this angle is 30 degrees. Now this is the velocity here. That should be tangential. This is the normal. This is 90 degrees. This is 60 degrees. Right? And if that is 60, this whole thing is also 90. So this is also 30 degrees. Perfect. Be careful with it. That means the particle is hitting the wall at 30 degrees, not 60. Just have to be careful with the geometry there. Because this whole angle is also 90 degrees, isn't it? This is a tangent, na? So this whole thing must be 90. Perfect. Then you're done. So this guy is hitting here with the normal at an angle of 30 degrees. So you'll bounce back with an angle of 30 degrees. The magnetic field is out of the plane. So QV cross B, yeah, it would go this way. This will actually, it'll have a force somewhat in this direction. 30, 30, na force will be like this. It will go in a circle like this. It will collide with this. Again, it will be velocity this way. Then again, it will go this way. Hey, it is going back now. It's going to the left side. Clear with this? Wait, I'll do one thing. I'll just put it into the. No, if you put into the plane, then it will be a problem that way. Okay, doesn't matter. So this thing is actually going to the left side, everyone. So let me start like this. So you start from here. You go like this. You collide. Then you bounce here. Then you go like this. Bounce here. Then you go like this. Then bounce here. Then you go like this. Yeah, you're getting this? It's just going like this. It's going to the left. All clear with this? The next thing, you need to get the angle. How to get the angle? Put a little geometry there. This is 30 degrees. You're going this way. Drop a perpendicular to this. This will be the force. So that will be the center. When you complete a circle and when you hit again here, again drop a perpendicular here. Drop a perpendicular here. Whew. So that whole thing must be 90. So this will be 60. This will be 60. So this will be 120. So that means you are covering an angle of 240. Therefore, time will be 2/3 of the time period. Yeah. What happens if E is 0? Any ideas? If E is 0, something interesting happens. The moment you hit, be careful. E0 does not mean you will get stuck. E0 meaning velocity along the normal becomes zero. So the moment this guy comes and hits here at an angle, this is 30 degrees. You have two components here. V cos 30, V sin 30. This becomes zero. Right? V cos 30, I wrote reverse. V cos 30, V sin 30. So this will still remain. So this will go in a circle like this of R by 2. Isn't it? V cos 30 will become 0, but V sin 30 abhi bhi hai na. So QV cross B, that thing will make you go in a smaller circle, which will keep grazing the wall. That's it. You will just be there. So you will go hit, and then you'll just go in a small circle forever there. You'll not stop. You'll not go anywhere. Okay with this? Suppose if E is equal to half, then what would have happened? You will hit. You will lose some velocity. Then it will be a smaller circle, smaller circle, smaller circle. But interestingly, what will happen? Eventually, you'll reach a circle which is again R by 2. Because every time you hit the wall, only the vertical component will keep decreasing, isn't it? The horizontal component will always remain same. So after infinity, your vertical component will become 0, only the horizontal component will remain, the circle will become R by 2. There you can play with different values of E there. Okay? So that's one way of playing around with this. Take a break. Come back in 5 minutes. We'll continue from here. So that's little about different particles, commotion and stuff. So let's see more. So we have a infinite solid cylinder. The radius is capital R. J is the current density. So current is flowing everywhere. It's a solid one. So remember in electrostatics, we used to use sigma and all. So here it is J. Find the magnetic field as function of small r. R is the distance from the center. Find the magnetic energy stored. per unit length from 0 to 2R. Now, because there is a magnetic field inside, there will be an attraction also. So that will lead to magnetic pressure as function of X. We have seen this in gravitation and electrostatics. So similarly, you also have something called magnetic pressure as function of X. Think of like this. If two parallel current wires are flowing, won't they attract? So if you treat this cylinder as a bunch of wires, all are trying to attract, isn't it? So the whole cylinder is trying to compress. So that leads to a pressure. Find force on one half of the cylinder due to the other half. Same question which we did in electrostatics that I think वहीं पे हमने sphere के लिए किया था याद है? Find the force on one half of the sphere due to the other half of the sphere. Idea was something similar. Yeah. There again, so it's a bunch of stuff all together in one question. So let's get this. If it is in the exam, maybe I would ask you B and D or B or C. A तो automatically निकालना ही पड़ेगा. The magnetic pressure is a good idea though. So we will see some questions on that in the next class. When I do elasticity, I'll teach you that. So we will see magnetic pressure, which will try to break the things and all that stuff, stress and breakdown, and we'll see all that stuff. We might spill over a bit. So next class also will continue with little magnetic field because anyway, I think elasticity and all really that there is really not too many different models anyways. So we'll mix it up with other chapters. Get them. I'll give you 4 minutes for ABC. Should have got the first two parts by now. So first part, what we do, we use Ampere's law. Take a Ampere loop at a distance r. So the Ampere's law is integral B dot dl is equal to mu naught I. Hope you remember, we have something called displacement current comes in mains ka thing, the portion. Should check that out for mains and bits. So displacement current comes when you have a time varying electric field. So this is the I crossing in this case. So this is B into 2 pi small r is equal to, this is mu naught into J into pi r square. Mu naught JR by 2. This is your magnetic field inside. For r greater than r, it will be simply like a wire at the center, mu naught I by 2 pi small r. Mu naught J pi r square. So outside it is 1 by r and inside it's a linear function. Yeah, if it's a mains or a bits question, they'll ask you for the graph. It will be a linear function, increases till there and then it decreases. Perfect. How do you find the energy? The magnetic energy density. If you remember in electrostatics, it is half epsilon E square. Here it is 1 by 2 mu naught B square. So you want the energy from 0 to this thing, so you have to be careful. So energy from 0 to 2r will be integral 1 by 2 mu naught b square. So mu naught j small r by 2 ka whole square. dv is the volume. So what is the volume here? You take a very thin cylinders. So at a distance x, you take a thin dx. So the volume of this will be 2 pi x L dx. That is the volume. The limits will go from 0 to r. So basically this term here is the energy stored inside the cylinder. Plus limits will go from r to 2r. You can actually do from r to infinity also, I guess. I'm not sure whether you will get something or... Yeah, 1 by r tha. So mu naught j r square by 2r whole square. नहीं, infinity नहीं ले सकते. You'll get a longer term. So it has infinite energy. 2 pi. This is x. This is x. Yeah, calculate this. This will be the energy stored up to r. Clear with this? Energy density ka thing. So that's how you get the energy. What about the pressure? See. So this is the cylinder. So at a distance r, we will take a small cylinder d theta with the dr. So we will take something of this sort here. So let me draw that piece. It would look like this. I'm exaggerating it. This side here will be r d theta. This side here will be dr, and this will be the length. You're getting the thin rod. So if you take a thin rod like this, that will be like a thin wire. This is the entire width, r d theta, dr, and l. So in this, we have a current I flowing. How much is that current? J into area, which is r d theta into dr. This is the current flowing through this thin section there. And this is experiencing a magnetic field B, which is tangential. So this B is something like this. So this is B, and these two are perpendicular. So this will give you a force IL cross B. So the force will act like this F. So how is this force acting? On which area it is acting here? This is actually inwards, huh? So basically this area there. So that is L into dr. Wait, I'm not drawing the picture properly. So it's actually tangential. B is that way and F is this way. Let me show it here. Wait. This is the current. This is how it will be. This is the magnetic field. The force will be actually towards inside. Making sense? IDL cross B. The force will be towards the center. So which area we are talking about? We are talking about this area, which is L, and this is R d theta. So your force is acting actually in this area. That is your force. So the pressure will be force by area. Force is L R d theta, and force is nothing but ILB. ILB. So LL will cancel. I will be J R D theta into dr. Sorry, this will be dp. Yeah? This will be the change in pressure. That's a small change in pressure on that side. This will be P into dA, and this will be P plus dP into A. R and D. R D theta. Perfect. What did I miss here? Wait, mixing up all the stuff. So let's calculate it. So force on the thin rod will be ILB. So I will be J R D theta dr. L is L only. And what is B ka value here? B ka value is mu naught J small r by 2. Perfect. So the pressure dP will be this force by area, which is L R D theta. That's a lot of work. J into dr mu naught J into r by 2. Integrate this. So pressure on the outer surface will be 0. So dP integral 0 to P mu naught J square by 2 integral r dr. So this limits will go from r to small r. So be careful with that. Pressure on the outer surface is always 0. And when you integrate this, you end up with pressure will be mu naught J square by 4 r square minus small r square. Yeah, you need to give a minus sign somewhere. So I think this is PdA and that is P plus dP. We always assume the pressure is increasing with this thing. Mu naught J square by 4 r square minus r square. That's a pretty good result. But that's how you derive. You take a thin rod and you do some working there. This is not a standard result. So if they ask you, this itself will be a question. Clear with this? I hope you're getting how did I take the element. I know my diagram was not great, but let me just try to show you the picture again. So this is how you're choosing an element from the center. I'll draw a big one for understanding. It's like a thin rod here. This is RD theta. So this is that arc there. So in this region, the current I is flowing. In this region, the magnetic field is B. Right? And the force is acting here. I hope you're able to see now. So you should take this area for the force. This length is RD theta. This length is dr, and this is length L. Are you clear? How did you take the element now? So that force on that shaded area is the pressure. So this is pressure into area. And from this side, you have pressure T plus dP into area. There, I think you can handle that. Clear with this? Question still not over. Now you want to find the force on the half side due to the other half. You can do with basic integration top view. If you remember, we did this thing in the solid sphere also. You can cut it in half, right? And now I know the pressure as function of x. So pressure will be mu naught J square by 4 r square minus small r square. So when you take the side view, right, the element has to be taken like this. So from the center at a distance small r, take a thin slice here. Of dr. So the force on the thin slice will be pressure into L into dr. You want the force integrate this thing. So mu naught J square by 4 R square minus R square L dr. Limits will go from minus R to plus R. Clear with this? Because the pressure is varying radially, you can just take an half cross section and you can find the force on that entire green ka thing. You will get it. But there is a faster way to do this. And you can do it faster way. Why? I'll just tell you one thing. Let's see if it clicks to you. This is mu naught J R power 1. Does it click to you? Told you multiple times. You see something R power 1, what it is, a linear function. You can use center of mass. The center of mass comes up. Can you give it a try? Think I'll give you a minute. So that idea is pretty good idea, right? Yeah, linear function there. You can use center of mass. Find the force on one half due to the other half using the center of mass ka thing. How will you use that is a different thing. You still have to figure it out. There's nothing like center of mass may put all the charge, it'll put all the current. It doesn't work like that. You will get some constant into RCOM. So what is that constant? You need to figure it out. Take a minute. So whenever you have to use RCOM, you have to take a general solution there. So let's take the top view. So from here, you're choosing some random point here. So on this random point, we have the magnetic field. The current is coming out. The force is inward. So on that small piece, if you try to find the force will be integral I, the length, which is dl, b, and anyway here it is sine 90. So this is the summation of all the forces, the vector form. The current I will be J into dA, that is your current. dl will be the total length of that entire rod, so that is L only, and the magnetic field is mu naught J R by 2. If you observe here, everything is constant, mu naught J square L by 2 integral R dA. Right? And you know this thing. So RCOM is nothing but integral R dm by integral dm. We can write this thing as sigma into R dA. Sigma into dA is the mass. Sigma into again dA. Sigma will cancel. You'll end up with integral R dA is integral dA. So you can write integral R dA is nothing but RCOM into dA is the area. So you can replace this whole stuff with, so the constant is this mu naught J square L by 2 into RCOM into that area of that whatever piece that you've taken. So in our case, you're finding for the half. So for this, it's an half disk. So when you see the top view, it's an half cylinder, which is an half disk. So RCOM will be 4R by 3 pi. And the area will be only pi r square by 2. Clear this? So you're finding for the cross section basically, because the L is already taken care of. Are you clear with the idea there? So this method, right, you need not find what is the pressure. So let's say they're just asking for energy and force on the one half, this would be a pretty good one. If they ask you pressure, you're dead. You have to find it. There's no other way. So you can handle this in both the ways. And if you see we did the exact same thing there, even in electrostatics. So yeah, helps now. It will come, it will not come, not sure, but yeah. But it's a good idea there to deal with it. All clear with this? But especially the pressure part, right? Make sure to go through the derivation. Do it on your own again. That the derivation is really good. This idea may click, might not click, but the pressure ka logic is pretty good because the pressure can be asked in gravitational pressure, electrostatic pressure, magnetic pressure, comes in 3 chapters literally. And once you know the pressure, right, you can relate it to fluid mechanics. And if you can relate it to fluid mechanics, I can do more. I will make up a question like this. I will say there is a gas sphere. A star is a made of gas. Assume it is an ideal gas, right? Tell me one thing. In a star, why does this gas does not fly away? Because of gravitation, isn't it? So a star is nothing but a gravitational sphere where it is filled with an ideal gas. And I will say assume the density of the gas is constant and assume it is an ideal gas. Find the temperature of the gas as function of x. So I'll use PV is equal to nRT. उसमें ये pressure लगेगा. That pressure will come from gravitational pressure. That's how you can find the temperature. From there, I'll ask you to find the internal energy of the star. That will come from integral F by 2 nR dt, internal energy. You can connect this to thermodynamics. You can do anything because you have pressure in the hand. You can play around a lot. So how it will morph, no one has no idea. But the pressure thing is pretty important. So make sure to go through the derivation. Because the pressure thing, next class I'll show you one more. For solids, it is a little different. For hollows, it is a little different. But hollow result is more easy to remember. We will see that also. But anyway, that is one thing. So let's see another type of model. This is another good one. First time when I saw the question, I think almost for 5-7 minutes, I was like, what the hell? But yeah, it clicked afterwards. So we got a cylinder. This is a long hollow. This is the front view I'm showing you, cylinder. Right? So this whole thing has a charge, sigma. Right? It is hinged in the center. So don't worry how it is and it is done. Mass m, radius r. Then what you did, you tied a rope and you connected a block M. Gravity is there. So string is wrapped around the cylinder and released from rest. It's a long, string. So don't worry, string will never end. So find the acceleration of the block. So as the block comes down, the cylinder starts rotating. Find the acceleration of the block. Take 2 minutes. Don't solve the question. 2 minutes first. Figure out what the hell is the cylinder doing. Spend time there. That is worth it. After that, kya karna hai, ideas will come. Don't worry about solving. Leave it. Take 3 minutes. Think what the hell is happening. It's a really good one. If the cylinder rotates, something happens. Don't start the problem without figuring out what happens. Get an idea. Oh, ये हो रहा है, ये हो रहा है, oh, इसलिए ये हो रहा है. Then start. You don't get that thing, there's no point in putting pen on the paper. No pressure. Take 2 minutes. There is no external magnetic field anywhere. This is all the data. Got a cylinder with a charge density sigma, mass m radius r, string is wrapped, other side you connect it to a block and you left it. Think for a minute more. Then I'll give you little things and let's see if it clicks. रोटेशन में I don't remember. This is let me ask you a few questions. As the block comes down, cylinder rotates. Agreed? Cylinder में charge है. So if a charge rotates in a circle, it behaves like a current loop. Current loops generate magnetic field. Current loops generate magnetic field. ठीक है? चलो. Now find out what is the direction of the magnetic field. And now if you have a magnetic field and if you have a charge, there will be a force. Just try to find the direction of it. That's not the answer, okay? Just try to find the direction of it. If this rotates, it will generate magnetic field. Because of that magnetic field, the cylinder में charge QEB will experience a force. What direction it is? See, so if the cylinder rotates this way with omega, so this behaves like a current loop I. So the magnetic field will be inward. So if you have a current I here and if you have a B inside, the force F will be this way. That means this entire cylinder is being stretched outside, isn't it? So if you take torque about the center, torque is 0. Isn't it? So magnetic field is not doing anything here. The torque due to the magnetic force is 0. That's not the problem here. So when I started maybe why pe stuck, I said, yeah, magnetic field is doing nothing. Then I said, what? Second thing, as it is falling, the cylinder will accelerate. Means omega is changing. If omega changes, current changes. If current changes, magnetic field changes. If magnetic field changes with time, what does it do? It creates an electric field, which is circular in region. Non-conservative electric field generate hoga from EMI, yaad hai? You'll get an electric field. Now this electric field can generate a torque, right? EQ. You get a tangential electric field. Are you getting the whole story? That is the story. That's what I'm saying. This should click. Once this clicks, question ho jayega 2-3 minutes mein. That part is a headache. So when the cylinder rotates, it behaves like a current loop that will generate a magnetic field. But this magnetic field is increasing with time, so it will generate a induced EMF. Because of that, you get an induced electric field. This electric field is circular in nature. That will create a counter counter torque on the cylinder. That's why this acceleration will not be a simple rotation problem. Now can you do? I'll give 2 minutes. This is a good one. This thing has solenoid ka result, induced electric field, current, rotational mechanics, 4 chapters. That's what makes this question really good. So there is a 2-3 layers there. I don't remember where I saw this question. Doesn't matter. As long as there's a good question, take it from anywhere. this thing now. We have a thing like here. So this is plus. Let's say this guy is rotating with omega. So if you have a cylinder, right, the whole thing is plus. And if this is rotating with omega, this is as good as having like a solenoid. Constant, these are like current loops. So the magnetic field due to the solenoid is mu naught Ni. So how do I compare solenoid to a cylinder? Write this thing as mu naught capital N I by L. So N into I is the total number of turns into the total current on the surface. So you can write it like this. N into I is the total current on the surface. So if you assume the cylinder has N turns, so N into I will be the total current on the surface, because I can't, this is easy to find. What is the total current on the surface? The charge, how much is the charge? Sigma 2 pi R L by time, which is 2 pi by omega. That's your current. This is your charge on surface. This is your time. Isn't it? That's how we find the current, right? Charge by current. So charge by time is this thing. So at that instant. So you can take a small thing and you'll get the same answer. So the magnetic field turns out to be LL will cancel, 2 pi will cancel, mu naught sigma omega r. Not a bad answer. This is the magnetic field as function of omega. Now, since we don't know, this guy will also have an alpha. It's accelerating there. Next thing, if you take the block there, the forces will be tension, mg, acceleration. Let me write one more on the next page. So I got D there, great. So on this cylinder, you will get a field E in the opposite direction. Kind of obvious. Why? If E comes in this direction, the cylinder will go faster and faster. Energy is not conserved. It has to be opposite. It has to slow down the cylinder. So, and there is a tension in the string here. So if you take torque about the center, that will be T into R minus E into Q. Q will be sigma 2 pi R L. That is your force into R is equal to mr square alpha. That's one equation there. If you take the block, we have tension, mg, and acceleration. So this will be mg minus t is equal to ma, and a is equal to r alpha. This is the three equations there. All clear with this? अभी इसमें क्या चाहिए था? If I can find E, my job is done, right? If I find E, my job is done. Now then comes your EMI. We know integral E dot dl is equal to d phi by dt. So this will be E into 2 pi capital R. Flux will be how much? The magnetic field B, area to anyway constant, pi R square into dp by dt. So E is equal to R by 2, but remember what was your B? B was mu naught sigma R omega, mu naught sigma R d omega by dt, which is alpha. Mu naught sigma R cube by 2 alpha. Alpha is your angular acceleration. Now you will take this guy from here and put it here. You know everything, right? I know E in terms of alpha, वो इससे जाएगा. Get T from here, dump it here. A is equal to R alpha, dump it there. You're done. You'll get everything you need. Yeah, it's lengthy, but you'll get it. And that too, I think you'll get alpha constant. That's the best part. So omega is increasing, but this thing will stabilize. You'll get a constant alpha. Clear with this? Yeah, that's how you can do this. It's a multi-layered problem. Like, okay, this is happening. First time, right? It's like, when you see the magnetic field, you think like, oh, this magnetic field is doing something. But then you realize the magnetic force is acting radially. The torque is not zero. Matlab, magnetic force is not doing anything. And then comes the realization like, okay, what the hell? Matlab, what is happening? Got the idea? Let's see one more like this. A little different one, but yeah, it's a good one. Let's say we have a large plate. So you need to know your magnetic solenoid, infinite radius of results. You should know. Especially this one, right? Converting a cylinder into a solenoid. This is a pretty good mains level question. If a charged cylinder is rotating, what is the magnetic field inside? So we got an infinite sheet, sigma. And all these things should be infinite and long. And this sheet is going with a constant speed v. On top of this sheet, you kept a block of mass m, charge q. Gravity is there. So this block is not slipping, okay? There is no slipping between the block. So it is going with the sheet. Great. Find the normal reaction between them. I can actually put a minus charge. I can ask you, find the speed when the block lifts off. This is little better, little easier than the previous one. But the theme is same. Something happens. So luckily, इसमें the induced electric field, all that stuff is not there. Do you guys remember field due to an infinite current sheet? Mu naught k by 2, where is the k is the current per unit width. So बस वही था. If you don't know that result, you'll be gone. Q mu naught v square. Square नहीं आता है रे. I don't know. Maybe आएगा. क्या पता. Let's see. हो सकता है. हाँ, you will get v square, right? V में big होगा. So what is the idea here? So when this sheet is moving, right? First of all, let's see the result. If you have an infinite current sheet, I think let me draw it that way only better. So it's like the current is flowing like this. So moving a charge, it moves like the current there. So there will be a magnetic field B because of this. The formula for an infinite current sheet is mu naught K by 2. K is nothing but the current per unit width. Right? So what width are you talking about? So this is the width here. So how do you find that? So if that is your width, consider a small section like this. Let this be dx. So current I will be the charge sigma into dx into the width w, that is your charge, by time. Time is dt. So that would be sigma v omega. That's your current. Sorry, w. So I by w is sigma v. This is your width. That's it. So the kk value is sigma v. So basically this is mu naught sigma v by 2. Clear with this? Magnetic field आ गया. बस हो गया equation then. So if you look at this thing, the forces are normal reaction, mg. Don't forget, there is also electrostatic repulsion QE, which is Q into sigma by 2 epsilon. And there is a magnetic field and there's a velocity here. So V cross B will be acting downward, QVB. Therefore, the normal reaction will be mg plus QVB minus QE. Got this? So because the sheet is moving, it is acting like a big current sheet. Because of the current sheet, there is a magnetic field. Now, if you want to bring that induced field ka thing, here it is difficult because if you can accelerate the sheet, you get a varying magnetic field. But problem ye hai, we studied only induced electric field for cylindrical magnetic field region, remember? So if you create any other type, we cannot calculate. So that is a problem. But if you accelerate this sheet, you will actually get an induced electric field also, which we don't know how to derive. But yeah, easy one. This is another thing. So we have x, y, z. So we have some weird shape here. Charge sigma. So due to this, the potential at the origin is V. And now what you did, you started rotating this with omega. Find the magnetic field at the origin. You will find it in the notes anyway. You can check out. It's done more neatly, but just a question there. So this rotates with omega. So you have some random piece. It is in the plane. Shape, give, nothing we know. We just know this thing is generating a potential V at the center. If it starts rotating with omega, find the magnetic field. हाँ वो ठीक है जैन, you'll get the answer now. What is the point of saying that? एडवांस में आए तो वही लिख लेना साइड पे. एंड ये क्वेश्चन ना we did in electrostatics में we didn't do. I said we will do it again. ये result था. This one. So you will need this in sigma r by pi epsilon. I'll show you. So I can frame a question like that. You can connect that and this. But how do we do this? Take a minute. Again, not tough, little different. These are the kind of questions you can expect. Like they're not mind-boggling, and these are little difficult to figure out. Once you figure out, it'll take like a minute or so. Right? So if you take any small piece here, random piece dq, Let the distance from here to here be r. So what is the potential? Integral k dq 1 by 4 pi epsilon dq by r. Remember, I don't know dq, I don't know small r. But I know what is integral dq by r. अभी magnetic field के लिए क्या होगा? So the current due to this small dq will be the charge dq by time 2 pi by omega. So because of this thing, it will create a small magnetic field, which is mu naught I by 2 r. So the magnetic field due to all these pieces will be mu naught by 2. I will be omega dq by 2 pi by 2r. So mu naught is constant, omega by 8 pi integral dq by r. So the magnetic field due to this small pieces is this. Now again, I don't know dq, I don't know r, but I know what is integral dq by r. So integral dq by r is 4 pi epsilon voltage. So mu naught omega by 8 pi 4 pi epsilon voltage. Pi 4 pi 2 mu naught omega epsilon v by 2. 2 नहीं आना चाहिए. kq by r mu naught I by 2r. यहाँ पे 2 बार लिखा था मैंने. Yeah. There you get a pretty good answer. So the magnetic field will be mu naught epsilon omega angular velocity. V is the potential at the point. So this is the relation between the magnetic field and the electric potential. So how will they ask you a question? They will say we have a big disk. It is hinged here. And they will say this whole thing is rotating about the circumference. And they'll ask you find the magnetic field at A. अब इसका potential याद है? We derived it. वो कितना था? Sigma r by pi epsilon. That's what we did in electrostatics. So you should know this result. And then you will say the magnetic field at A will be mu naught epsilon omega this sigma r by pi epsilon. So then you can bring electrostatics and you can mix up with this. Clear with this? So idea is that you have to use that integral dq by r to figure it out. All clear with this? Let's see one last one. This is also a good one. Not again too tough, not too many steps, but yeah, you have to think. So we got a ring here. Mass m, radius r. It's on a smooth floor. Gravity is present. Okay, I'm not drawing the floor. So from the center, we are having a magnetic field which is radial. If you see the top view, this is how B is going. This is the top view. Yeah, both look the same anyway. Fine. Now what you did, you took a small charge Q and you just passed it around. You can ask, how can I do this? Maybe put a capacitor here and you just close the switch. What will happen? Capacitor will suddenly discharge, right? So you'll get a charge Q flowing through the loop. A charge Q is suddenly passed. In very small time. Find the maximum height of the ring. Find the H max of the ring. Something happens and the ring flies. Find the maximum height of the ring. And I hope you guys remember when I taught you in the class, right? I told you always, look at the words. Very small time. These are the words. The moment you see the word very small time, these are based on impulse. So this is one more variety of questions. You'll keep hearing this thing. Something happened in a small time, something went in a small time, current went in a small time. You hear that small time word, it is understood. It's a very small time interval. It's an impulse-based problem. अब impulse क्या है? You have to figure it out. So when you send a charge Q suddenly, how much time we don't know. Something happens and the ring flies into the air. Find the maximum height of the ring. The magnetic field is radial, B. Mass M, radius R, yeah, all that stuff you want. Why is the radius required? I don't know. I just gave it, I guess. You don't require. रिंग है तो मैंने सोचा चलो दे देते हैं रेडियस आर. You guys figure it out. So this is how you have to think. Okay, charge Q is going in a very small time. So that means Q by time is very big. Matlab, the ring will feel someone sent a huge current for a small time, isn't it? Someone sent a huge current for a small time. That is the meaning of Q went in a small time. And if a current is flowing in a magnetic field ILB, so that means I is big, so F is big. So this ring will experience a large force for small time, means it will feel someone kicked it with a huge force for a small time interval. So if you look at this thing here, so this is the current. This is your magnetic field B. Radial, no? It's not up to scale. I should draw it somewhere else. Wait. This is your B. This is your current. These two are perpendicular. IL cross B, the force will be up. Check it out. You look at any point here, current, magnetic field, current, magnetic field. You will notice all these forces are acting up only. That is the reason I gave the radial field. So F is equal to ILB. L is 2 pi r ना रे, यहाँ पे रेडियस लगेगा. I don't know the current, but change in momentum is integral f dt. That would be 2 pi rb integral I dt. You don't know the current, you don't know the time, but you know the I dt ka value, which is 2 pi rb cube. This is m into v. This will give you the velocity. H max is equal to v square by 2g. Clear with this? That's it. Getting the idea, after that it is easy to solve. So this ring will feel someone kicked it with this much velocity, then it flies up. These are some pretty good ones. When we do EMI, again, you'll encounter things like this. So small charge went, small current came. So these are some good ones, right? We still have a few more pending. So I think Monday when we catch up also, we'll do a few more of this before going ahead with the next chapter. Anyway, for elasticity and properties of matter, we have 2 classes. Okay, with that, we will wrap up for the day. And I'll see you guys again on Monday. We'll continue from here. So any doubts, anything else, please stay back and ask, or else you're free to leave.
Sir, on this page,
Yeah.
if we take